This is Logic and Computer Design Fundamentals, and we will talk in Chapter 1 about digital computers and information. As an overview, we will see digital system and computer systems, what's the information representations, and then we will talk about the number system. We will focus on binary, octal, and hexadecimal. After that, we will move to some basic arithmetic operation. We will see the base convergence between those number systems. And we will talk about decimal code, specifically BCD, the binary coded decimal, and some application of parity. After that, we will talk about the gray code and alphanumeric codes. So the digital system, it takes a set of discrete information, which is the inputs, as you can see here, and takes also a set of discrete internal information, which is the system state here, and produce or generate a set of discrete information outputs over here. This is what we call the discrete information processing system. The system state, sometimes it existed and sometimes it doesn't. To explain this further, the type of digital systems, either it doesn't have states, so no state present. And this is what we call the combinational logic system. As you can see, this is the combinational logic. It have inputs and produce outputs. Or in another way, we can say the output is equal to the output is a function of the inputs. This is the first type. The second type is when the state exists or present. As you can see here, we have a combinational logic, as we described previously. We have inputs and outputs. Now we have what we call storage elements. It saves the current state. So it gives the combinational logic the current state along with the inputs. And then after it's do its processing, it generates the output and the next state. So looking at the storage element accepts the next state and produce the current state. So if the state is existed, the state updates at discrete time. If that's happening, then we call it a synchronous sequential system. If the state updates at any time, then we call it a synchronous sequential system. This figure here shows you the difference between the synchronous and the asynchronous system. The synchronous system, you have a certain request, but the update happens on only a specific time. As you can see, those dash lines, they have certain period. After the same amount of time, at the end of that period, you do the update. So if the request happens at any time here, the updates happen only at the end of this period. For example, and then the other period, the request happens here, the updates only happens at the end, and the last period or the third period, the request happens here and the update happens at the end. This is what we call a synchronous system. To generate those periods, we use what we call a clock. And we will discuss this further when we talk in details about the sequential circuit. The asynchronous sequential system, as the figure suggests, you can see that when you have a request, the updates happen at the same time. So the clock or the period doesn't govern the relation between the request and the update. Now, as we say here, when there is no state presented, the output is a function of the input. When the state is existed, we have to get the state function and also the output function. So the state is actually a function of the state and the input, while the output is a function of the state. It could be this way, and that's one type, or it could be a function of the state at the input, which is similar to what we seen in the state. You can also see this from the figure. As an example of digital systems, this is the first example. You know, this is the counter. It's usually seen in cars. And it has some buttons along with it, or sometimes in another way, either you count or you do the reset. If you click the reset, it zeroes everything. And if you click the count up, the count starting moving up. This is in general. In cars, of course, you don't have this. It depends on the mileage that the car have. So the digital counter, or what we call odometer, it has inputs here, as you can see, count up and reset. It has output, which is the visual displays. You see the numbers. And it has the state, which is the current value stored by showing here in the digits. So the current state is, for example, 001356 and 4. If you were asked, is this a synchronous system or a synchronous system? It depends on the system. If it has a clock, a periods that govern the relations, then it's a synchronous system. And this is usually the case. If it doesn't, then it is a synchronous system. This is another example of a digital system, which is the computer. You can see here, it has several input devices, like, for example, keyboard, mouse, modem, microphone. In the picture here, you can see the keyboard. It's an input device, and it goes to the what we call the bus, and the bus distributes the binary information or whatever data is there to other subsystems. It has also output, for example, CRT, LCD, modem, speakers, and other examples. As you can see, as an output device, we have the LCD screen. In an abstract view, it has the computer has a CPU, which has control unit and data path. And there is an exchange between the control unit and the data path. When you want to get values to process them, you get them from the memory, you read them from the memory. After you've done with the processing and you want to store the value or the output result, you store it in the memory. So you load and store, or you read and write. Similar thing or similar behavior with the input or the output devices, as you can see what we've seen in these examples. Of course, there are other systems. It's good to mention them right now. So here you have the bus that distributes the data between the systems. We have the processor. Inside the processor, we have the CPU, which is the central processing unit. We have the FPU, the floating point unit. We have caches. Usually it has levels, level 1 cache, level 2 cache, level 3 cache. And we have also some other modules like the MMU. And we here have an external cache, usually level 1 and possibly level 2 is internal. Level 3 is usually external. We have also the RAMs, which is the main memory here. You can see we have 4 different cards with usually similar sizes, and it's connected to other devices. For example, here we have the graphics adapter, we have the drive control. The drive control the hard drive, and get the information from the hard drive at the beginning, move it to the RAM, and from the RAM, it moves to the cache, to other caches, and then at the end to the CPU for processing. The main input, you get it from the keyboard, and when you're done with the processing, you show it in the LCD screen. So now it's good to define what are the signals. The signals is an information variable represented by physical quantity. For our digital systems, the variable takes on discrete value. In our case, it has only two values, two levels. This is why we call it binary values. Bi being meaning two. Binary values are the most prevalent values in digital system. And here are some examples of how to differentiate between those two values. So if you has the representation method as digits, the first binary value is 0, and the second binary value is 1. And this is the most famous representation. We call it 0 and 1s. It could be words, in words, like, for example, false and true, or low and high. Especially we'll have this in timing diagrams. Or words, which is, for example, off and on, like a switch. Binary values are represented by values or range of values of physical quantities. When we are specifying the binary system, we have only two values, the first binary value and the second binary value. This is the signal examples over time. So we have this is the time axis, and after a certain period of time, if you have a signal as shown here, this is called analog signal. Usually it's continuous, as you can see here, or digital, which has discrete values, right? For example, here you have only 0 or 1, while here we have also 0 and 1 and so on. This is asynchronous system. You can see that it doesn't change its values on those predetermined cycles, like here, here, and here, and here. The change happens at any point of time. So it's discrete in value and continuous in time. And the synchronous, it's discrete in value and time. You can see that the value or the change happens only in those discrete times. Also, as a signal example, we want to discuss the physical quantity or the voltage. You can see if we have two circuits, circuit 1 and circuit 2, and if we assume that there is an output coming out of circuit 1 going to circuit 2 as input, so this output range is ranged from 0 volt to 1 volt. We will assume that from 0.0 to 0.1, we call it a low digit. And from 0.9 to 1, we call it a high digit. So we have low and high, or we have logic 0 and logic 1. So any value that is between 0.0 and 0.1, we consider it a logic 0. Any value between 0.9 volt and 1 volt, we consider it a logic 1. You can see that in the output, we are restricting this range. It's very small here and also here. Now, this is what coming from the output. We only allow those values to be logic 1 and those values to be logic 0, and now they are coming out of the output. At the end, they will get to the input after some time moving through this line. When it's moving through this line, it might have certain noise, certain environmental effects that fluctuates its value. This is why in the input, we consider from 0.6 volt to 1 volt as high or logic 1, and from 0.0 to 0.4 as low or logic 0. You can also see here if it's time-dependent voltage. So this voltage, it goes between any value from 0.0 to 1 volt. Could be 0.0, 0.1, 0.2, 0.53, whatever value it is. So it could be any value in voltage. But at the end of the day, we would say, okay, this value here, since it's follow this range, we call it 1 or logic high. The values here, we will consider it logic 0, and so on. This is the binary model. There are other physical quantities other than 0 and 1. We mentioned some of them in the previous slide. And the CPU, it depends on the voltage. The disk depends on the magnetic field. The CD, it depends on the surface bits, and it's affected by light. And the dynamic RAM, especially if it's dynamic, the dynamic type of the RAM, it depends on the electric charge stored in a capacitance. The number system representation, to represent numbers, we have to define what we call a radix R. So the numbers that we all know is it has the decimal radix, which is power of 10. A number with radix R in general is represented by those string of digits. You can see the point here, this point. At the left of the point, we have digits A0, A1, A2, up to AN-1. And to the right of this digit, we have A-1, A-2, up to A-M. Each one of those positions have a certain power, which is, in general, radix to the power of 0, radix to the power of 1, radix to the power of 2, and so on, up to N-1. This is on the left side of the point. On the right side, we have radix to the power of -1, radix to the power of -2, up to radix to the power of -m. Now, this digits from A0 to AN-1, it could have any value between 0, including the 0, up to R, but excluding the radix R. And we have this point, we'll give it a special name, which is the radix point. So any number to a certain radix R is equal to the summation of A0 multiplied by R0 plus A1 multiplied by R1 plus A2 multiplied by R2, and so on, up to AN-1 multiplied by RN-1. That's what we call the integer portion of the number. We add to this value the fraction portion of the number, which is again the same idea, A-1 multiplied by R-1 plus A-2 multiplied by R-2, and so on, up to A-M multiplied by R-M. And this mathematical equation shows what we described right now. So let's have example of certain radix that are important to us in this class. This is digits from digit 0 to digit 5. So we have 0, 1, 2, 3, 4, and 5. This is in the positive side, and the negative side, we have -1, -2, -3, -4, and -5. And we want to represent these numbers in certain radix. Now, in a general radix R, we have R to the power of 0, R to the power of 1, R to the power of 2, and so on, to the R to the power of 5. And also on the negative side, R to the power minus 1 up to R to the power of minus 5. In the decimal system, if our R is equal to 10, so R here is equal to 10, now the digits, it has to be between 0 and 9. And if R is equal to 2, which is a binary system, we have only 2 digits, which is 0 and 1. So now, if the power is R to the power of 0, so 10 to the power of 0 is equal to 1. 10 to the power of 1 is 10, 100, 1,000, 10,000, 100,000. And those what we have in the decimal system. If I have a number, let's say 123.567. So this location is 10 to the power of 0. This location is 10 to the power of 1. And this location is 10 to the power of 2. This location, or this position, is 10 to the power of minus 1. And this one is 10 to the power of minus 2. This one is 10 to the power of minus 3. So now this is like more numbers. So we have 1, 10, 100, 1,000, 10,000, and 100,000 going from power to the 10 to the 0 up to 10 to the power of 5. Also, in the negative powers, we have, if we have 10 to the power minus 1, it's 0.1. To minus 2, it's 0.01. To minus 3, 0.001, and so on, to until you have 10 to the power of minus 5, which is 0.0000 and 1. Now, in the binary, and this is very important in our class that you memorize these numbers, 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16, and 2 to the power of 5 is 32. That's when the powers are positive. And you can also continue. In the negative side, we have 2 to the power of minus 1, which is 0.5, 2 to the power of minus 2, 0.25, and 2 to the power of minus 3 is 0.125, 2 to the power of minus 4 is 0.0625, and 2 to the power of minus 5 is 0.03125. Now we have special power of 2's, which is 2 to the power of 10, 2 to the power of 20, 2 to the power of 30, and 2 to the power of 40. 2 to the power of 10 is what we called a kilo, and we denote it by the letter capital K. 2 to the power of 20 is the mega, which is denoted by M. 2 to the power of 30 is giga, which is denoted by G. And 2 to the power of 40 is tera, and denoted by the letter T. If you want to find these values, you can use a calculator, and you see that 2 to the power of 10, which is 2 multiplied by itself 10 times, it's 1,024. 2 to the power of 20 is 1 million something. 2 to the power of 30 is 1 billion something. And 2 to the power of 40 is 1 trillion. 1 trillion something, as you can see here. So it goes thousands, millions, billions, and trillions. Now, if we consider only the positive powers, in the previous example, we were having from 0 to 5. Now we will continue 2 to the power of 0 up to 2 to the power of 20. And we will see these numbers because it's very important to try and memorize them. 2 2 to the power of 0, the value is 1. 2 to the power of 1 is the value is 2. So we have 1, 2, 4, 8, 16, 32, 64, 128, 256, and 512. And then we have the kilo, which is 1024. We have also 2K, which is 2 to the power 11. That's 248, 2048. 2 to the power 12, that's 4096. And 2 to the power of 13, 8192. And you can see after this, up to this point, you have to memorize them really good. You have to have this in the back of your mind without using the calculator. After this, you can see that 2 to the power 14, you can break it down to 2 to the power of 4 times 2 to the power of 10. So you know that this is a kilo. 2 to the power of 10 is a kilo. 2 to the power of 4, you memorize it already, it's 16. So this is 16K, 32K, and this is 64K. But if you calculate it, it will be 65,536. 2 to the power 17 is what you see here, 18 is here, and 2 to the power 19 is here. And then 2 to the power of 20 is one of the special power that we just mentioned, which is the 1 million and something. So that's a million in the binary system, which we call a mega. If we say million, then that's a decimal system. If we say megabyte or megabit, so this is binary system, becomes a binary system. Okay. Now, let's see the other bases, or the basis that we will focus on our study. We already mentioned the decimal and the binary. In the binary, we have radix, which is 2, and we have only 2 digits, 0 and 1. You can see that the digits starting from 0, and you continue counting until you reach the radix. You reach the radix, but you don't include it. So you say 0 and then 1. In the decimal system, the radix is 10, and we have the digits 0, 1, 2, 3, 4, up to 9. Now, if we want to continue counting, we would say, okay, we will move to the other digit, which is 10. 10 is composed of 2 digits, the digit 0 and the digit 2. So 10 by itself is not a new digit. So that's the binary system and the decimal system. We have other systems like, that are used usually with computers, which is the octal system, and the radix is 8, and the hexadecimal, and the radix is 16. You can see that the digits here is starting from 0 up to 7, and the digits here is starting from 0 up to 15, which is less than 16. However, what we do is we have the following digit, 0, 1, 2, 3, up to 9, and then after 9, we use letters. So A corresponds to the digit 10, B to the digit 11, C, D, E, and then F. So this will be considered 10, 11, 12, 13, 14, and 15. But we don't write 10, we write A. In the hexadecimal, we don't write 10, we write A. For example, if you have the value 15 in decimal, we write it in hexadecimal as F. Now, let's see different numbers with different bases, so you know what we mean. So if we say we have a decimal system and we have those numbers, we have 0, 1, 2, 3, 4, 5, 6, and 7, 8, and 9, and you can see here that the digit 0 in the left side means nothing to us, as you know the decimal system. And after the 9, we have 10, 11, 12, 13, 14, 15, and 16. Now, if you want to represent the value 0, 0 in the binary, it will be 0, 0, 0, 0, 0. The 1, we have a 1 here, and 0, 0, 0, 0. Now we have 2, and we have only 2 digits in binary. So we need to figure out a way to present the decimal number 2 in binary. And we represent it, as you can see, by 0, 1, 0, 0, 0. Actually, there is a quick way to fill this column, which is like this. We will start with saying 0, 0, 1, 0, 1, 0, 1, 0, 1, and we keep flipping 0, 1, 0, 1, and so on until we reach to the last one. And in the next column, we will start with 0, 0, and then 1, 1, 0, 0, and then 1, 1, 0, 0, and then 1, 1, and so on. The third column, we will have 4 zeros, 0, 0, 0, 0, and then 1, 1, 1, 1, and again 0, 0, 0, 0, and then 1, 1, 1, 1, and so on. The next digit, we will have 8 zeros, 0, 0, 0, 0, 0, 0, 0, 0, and then 8 ones, as you can see here. And then we start flipping again for the next 8 digits. The last digit, which is the 5th digit here, we will have 16 zeros. As you can see, every digit here is 0. And after you have 16 zeros, you'll start having another 16 ones, and so on. So you can see now, for example, if we have this number 5, the digit, the binary representation of the decimal number 5 is 10100. The binary digits, for example, the decimal number 12 is 00110, and so on. The octal, if we have the octal representation, you can see that we will follow the similar rule. We will start with, now previously in the binary system, we have only two digits. So we have 0 and 1s, only 2 values, 0, 1, 0, 1, and so on. Here we have 7 values in the, or 8 values from 0 to 7 in the octal. So we will start from 0, 1, 2, 3, 4, 5, 6, 7, and then we start again 0, 1, 2, 3, 5, 4, 6, 7, and then again we continue. And the next digit, we have zeros for 8 times, and then 1 for 8 times, and then 2 for 8 times, and then 3 for 8 times, and so on. The hexadecimal, we have 0, 1, 2, 3, 4, 5, 6, 7. We continue 8, 9, and then we have A, B, C, D, E, F that we just defined. When we reach F, we exhausted the value from 0 to 15. What to do with 16? We start again from 0. And then we continue 0, 1, 2, 3, up to F after this. In the next position, we will start with 0 for 16 times, for all the 16. And after this, we have 1. And as you can see now, in the decimal, we started from the value 0 up to 16. We can say from 0 to 16. But in the hexadecimal, you can't say that this is 10. If you say 10, we assume that this is the decimal system. This value is 0, 1 in hexadecimal. 0, 1 in hexadecimal. So these are the simple number representation. We started only from 0 to 16. But what if we have a big number? Is there a way to know what exactly is the decimal value if this number is represented in binary or octal or hexadecimal? There are ways, and we will describe them in the next slides. So we'll first try to convert from binary to decimal. Why we started with this? Because we know the decimal system. This is the system that we are familiar with, and we use it in everyday life. So we will try to convert from a binary number to decimal to know its value. So to convert to decimal, we use the decimal arithmetic, or we use this mathematical representation, which is the summation of the digits, of the current digits multiplied by its respective power of 2. So for example, if we have this number in binary, and you can see that if you see this number and you try to check it in this table, you can see that this is not in the table. 0, 1, 0, 1, 1. If you try to find it in this table, it's not there. So what to do? We cannot use the table. To convert it to decimal, we should know that this position here, this position, this is the same number. This position is 2 to the power of 0. And this position is 2 to the power of 1. This one is 2 to the power of 2. And this one is 2 to the power of 3. And this one is 2 to the power of 4. Or you can memorize it in another way like this. This position is 1. This one is 2. This one is 4, 18, and 16. This would be the weight of the position. This is the weight of the position. It's 1, 2, 4, 8, and 16. So what to do? If there is a 0 in the position, you don't add its power value. So we cross this because there is a 0 here, and we cross this. We only care about the position that has the value 1 in the binary system. So what do you do? We add 2, 8, and 16. And if you add them together, 16 plus 8 plus 2, it's 26. This is a quick way of representing this. To get this in detail, you would say, okay, we have 0, 1, 0, 1, 1. So we'll have this 0 multiplied by 2 to the power of 0. We're trying to do this, the summation of the digit multiplied by its respective power of 2. This is 1, which is this one, multiplies by 2 to the 1. This is 0, multiplies by 2 to the 2. This is 1, multiplies by 2 to the 3, to the power of 3. And this is 1, multiplies by 2 to the power of 4. And then we add them together. You can see that this is 16 plus 8 plus 0 plus 2 plus 0, which is 26. That's another value here, which is 1, 1, 1, 0, 0, 1. Similar idea. But here I'll try to do it in a quick way. We will care about only the ones. So we add 1, 2, 4, and 32. You should know, for example, this one, its position is, this is the power of 0, power of 1, power of 2, power of 3, power of 4, and this is the power of 5. So it's 2 to the power of 5, which is 32. This is a quick way to find the 32. Once you have those ones, you add its respective power, 1 plus 2 plus 4 plus 32. And if you add them together, it's 39 and decimal. You can go back to the table that we just saw. For example, let's pick a very easy number. Let's say 9. So is this really the binary representation of the 9? Yes, because this is 1 plus 8. 1 plus 8 is 9, and so on. You can check other values in the table as well. So this is the quick way that I just mentioned. This is the long number in binary. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits. A binary number with 10 digits, or what we call it 10 bits. It has 10 bits. So here we only consider the ones. And you can see that this is the power of 1, or its weight is 1. Its weight, this one is weight is 16, and this one is 64, and this is 512. If you add them together, it will be 539 and this. And this is the way to convert from binary to decimal. If we want to do the opposite conversion, which is from decimal to binary, there are two methods. I will show you both methods, and then I will suggest the method that we use. The first method, if you have a number in decimal, for example, this number, 625 in decimal. So the radix, its radix is 10. We subtract the largest power of 2. That gives a positive remainder. And then record this power. If it's 2 to the power of I, then we record the I. So we do this. To do it in this example, we have this number, 625. What is the largest power of 2? If we subtract this number from this power of 2, it gives a positive remainder. We can't say that it's 1024, which we can't say it's 2 to the 10, which is 1024. Because if we subtract 625 from 1024, we do this subtraction, 625 minus 1024, you will get a negative remainder. The result will be negative. So the largest number that gives you a positive result is 512. And if you do the subtraction here, you will get 113. But what you care about is the power, which is 9. Because the 512 is 2 to the power of 9. Now we do the same thing. You start repeating, subtracting from the prior. You take the prior remainder is 113 here, and then you subtract it from the largest power of 2. That gives you a positive remainder. So here 113, you can't say 2 to the power of 7 because it will be 128 and it will give you negative. The largest one is 2 to the power 6, which is 64. 113 minus 64 is 49, and the power that we use is 6. We do the same thing with 49. We will subtract it from 32, which is 2 to the power of 5. So the power is 5. The result is 17. 17 minus 2 to the power of 4, which is 16, is 1. And the power that we have is 2 to the power of 4. And then you reach usually to 1. 1 minus 1 is equal to 0, which is, this one is 2 to the power of 0. These powers is actually the positions of the ones. So what do? You place 1 in the position in the binary result, which corresponding to the recorded power that you recorded here. And in all other positions, you place a 0. So here we would say, okay, we got in the power of 0, we recorded, so we put 1. 1 is not there, we put 0. 2 is not there, we put 0. 3 is not there, we put 0. 4 is here, so we put 1. Also 5 and 6, we put 1 and 1. 7 and 8 are not there, so we put 0, 0. And 9 is there, so we put 1. And this will be the binary result. So the conversion from 625 in decimal to binary system, the binary result is what you see here. To do this, you have to memorize the power of 2. We mentioned this before, and we mentioned this also now. Now you can see 2 to the power of 0, 1, 2, 3, and 4. This is 1, 2, 4, 8, 16. 2 to the power of 5 up to 2 to the power of 9. This is 32, 64, 128, 256, and 512. You have to memorize those. Also, you can record them this way. You can see that the red boxes are the powers that were recorded here. That's the first method. So to summarize this method, or to give it a name, we repeat subtracting the largest power of 2. Or simply you could say repeated subtraction. That's the first method. The second method, we convert the integer part, and we also it can also convert the fraction part. In the previous method here, we only focused on the integer part. You could do the fraction part, but it's not gonna be so easy. So in the second method, we do the conversion for both the integer part and the fraction part, and this is what we usually going to use in our class. To convert the integer part, you repeatedly divide the number by the power of 2. Or you repeatedly divide it by 2, the radix that you have, which is 2. You repeatedly divide it by 2. And then after you get all the remainders, you record them in a reverse order to generate the binary representation. For the fraction part, you do actually the easy way, which is you multiply by 2. And then you record the result. After you record the result, you record them in order. So to summarize this method, you convert the integer part by dividing by 2 and record the remainder in a reverse order. To convert the fraction part, you multiply it by 2 and record the integer digits in order to get the fraction part. To explain this, I'll show it to you in an example. So let's say you have this number, 46.6875. This is in decimal. And you want to convert it to binary or base 2. So what to do? You take this point, and this point is differentiating between the integer part, which is the 64, and the fraction part, which is the 0.6875. So what to do is every time you divide by 2, you can see that you divide by 2. In the other step, you divide by 2, you divide by 2, and so on. While in the fraction part, you always multiply by 2, multiply by 2, multiply by 2, and so on. To do this method correctly, in the integer part, you say 46 divided by 2, that's 23 with a remainder of 0. You can also think about this. Okay, you always divide by 2. So if it's an even number, then for sure the remainder is going to be 0. While if it's an odd, then the remainder is going to be 1. So we divided 64 by 2, it becomes 23. Now we take this 23 here, and we divide it by 2. It gives us 11 with a remainder of 1. Now we take this 11, we divide it by 2. It gives us 5 with a remainder of 1. You have 5 divided by 2. It gives us 2 with a remainder of 1. You divide this 2 by 2. It gives us 1 with a remainder of 0. And then you take 1 divided by 2, and this is the last step. It gives us 0 with a remainder of 1. Now you got the result in a column this way. How to record it? How to record it? You record it in a reverse order. So you do it this way. You can start this from here, from 1, and you start recording 1, 0, 1, 1, 1, and then 0. So this is the 1. Then you record the 0, and so on. You record the ones, and you continue. So you start in a reverse order. This is the integer part. The fraction part, you multiply by 2. Now, if you multiply by 2, you can generate a pure fraction or a fraction with an integer 1. If you multiply 0.6875 by 2, it becomes, or it equals to, you multiply this by 2, it equals to 1.375. You can also think about it this way. If the number is higher, is 0.5 or higher, it's gonna definitely generate a 1 for you here. If it is less than this, or less than 0.5, then it's going to generate a 0 for you. So now you have 0.6875 times 2 is equal to 1.375. You take only the fraction. You keep this one here, and you take only the fraction, and you multiply it by 2. It becomes 0.750. You take the fraction only, multiply it by 2, it's 1.500. You take the fraction, and you multiply it by 2, and gives you 1.0. Now, if you take the fraction, it's going to be zeros, and you stop. Now, what to do to record it? You start in order of the operations. So you say 1011, and you record it this way, 0.1011. Now, what to do? At the end, you combine the integral and the fractional part like this. You take this part here, point, and you take this part here. And this is going to be the full conversion. This is the second method. And I suggest in our class that we always use the second method. Now, to check the conversion, one easy way is to convert back. So if we want to check this conversion that we just did, we know that this is the integral part after we did the conversion, and this is the fraction part. So what to do? Convert it back. If you convert it back to decimal, you would say, okay, I'll only consider the ones, and this is the 2, 4, 8, and 32. If you add 32, 8, 4, and 2, it becomes 46. So the integral part is correct. For the fractional part, you will say that it is this one, and this one, and this one. This is multiplied by 2 to the power of 2. 2 to the power of minus 1, sorry. And this is 2 to the power of minus 2. And this is 2 to the power of minus 3, 2 to the power of minus 4. Let me write it down. It's 2 to the minus 1, 2 to the minus 2, 2 to the minus 3, and 2 to the minus 4. We consider only the ones. So we consider the half, 2 to the minus 1, which is 1 over 2, 2 to the minus 3, which is 1 over 8, and 2 to the minus 4, which is 1 over 16. You get the value for each one of them. You add them together, it becomes the fraction that you have. This is the way to confirm that your conversion is correct. That's another bigger example. We do it the same way. I'll just mention some, you can take this as an exercise for you. I'll just mention some pointers here. This is an odd number, so the remainder must be 1. An odd number, remainder is 1. Odd number, remainder is 1. Even, the remainder is 0. Odd, the remainder is 1. Odd, the remainder is 1. Odd, the remainder is 1. Same here for the even. They are all even, so they are zeros. And the last one is odd, so the remainder is 1. And you do it in the reverse order when you record the number. And here, this number is bigger than 0.5. So there must be an integral part here. There must be a 1. This is less than 0.5. It's a 0. 0.8, it's a 1. 0.6, more than 0.5, it's a 1. 0.25, less than 0.5, it's a 0. 0.5 exactly. So it's a 1. And you can practice the same method. You will find that this is the fraction part here. And this is the integral part, which we found here. Now, here we will discuss the conversion to decimal from other bases. We did mention how to convert from binary to decimal. And for example, this example here, we consider only the ones and we take its weight, which is, or its position power of 2. So this is 1 plus 2 plus 32, which is 35. Now, if we have an octal base or hexadecimal base, and we want to convert to decimal, can we do it using a similar way to the binary? Yes. How? Now, the weights are different. As you can see in the binary, the weights is 1, 2, 4, 8, and so on, which is the power of 2. Now we will have the power of 8 in the octal system, and we will have the powers of 16 in the hexadecimal system. So now, if we have this number in octal, and it has 6 digits, we have the power of 8, 1, 8, 64, 512, 4096, and so on. So this is 8 to the power of 0, 8 to the power of 1, 8 to the power of 2, 8 to the power of 3, 8 to the power of 4, and 8 to the power of 5. If we have this number, for example, to get the decimal value, the equivalent decimal value for it, then we will multiply 6 by 1, 4 by 8, 2 by 64, 7 by 512, 3 by 4000, and 69, and the last digit was 0 to this power. And then you can stop here, because any 0 to the left is not considered. And then you add them together, you will get the value in the decimal. Alternatively, without memorizing these powers, you can say 6 multiplies by 8 to the power of 0, which is 1. 4 multiplies by 8 to the power of 1, which is 8. 2 multiplies by 8 to the power of 2, which is 64, and so on. And then you add them together and you get the result in decimal. In hexadecimal, you will have a power of 16s. So 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, to the power of 3, and so on. If we have this number, for example, 7, F2, and 8. We have letters now in the digits. What we know in hexadecimal, A represents 10 in decimal. F represents 15 in decimal. So what we do, we say 7 multiplied by 16 to the power of 0, which is 1. F multiplied by 16 to the power of 1, which is 16. 2 multiplied by 16 to the power of 12, which is 256. And A multiplied to the power of 16 to the power of 3, which is 4096. In your calculator, you can multiply 7 times 1 and 2 times 256. But you don't find A and F. What to do is you represent A by 10 and F by 15, which is its equivalent decimal value. And then you get the result by adding those terms, and you get the decimal conversion. Now, if you were asked to convert from octal or hexadecimal to binary, now from the previous slide, we have decimal. Always we were dealing with a decimal. Either you convert from binary to decimal, from decimal to binary, from octal to decimal, from hexadecimal to decimal, and so on. There is a decimal always there. But what if you were asked to convert from octal or hexadecimal to binary? What to do? Actually, this is one of the easiest conversions. In octal, you will portion your binary number as 3 binary digits. So if you have this number, or in octal, you will consider everyone as a 3 binary digit. Every one of them 3 binary digits, and so on. So you will restate the octal as 3 binary digits, starting at the radix point, and then you will go to the left to get the integral part, and to the right to get the fraction part. Let's say this example here. So we say, okay, 3. I know that the 3 is represented by 110. To get this quickly, you have to memorize the table that we mentioned before, which is this table. You could know that the 3 is 1, 1, 0. You have to memorize it instead of doing the conversion. You can also convert if you want. So we have this 3 is 1, 1, 0. You will represent it as 1, 1, 0. 2 is 0, 1, 0. The 5 is 1, 0, 1. And the 6 is 0, 1, 1. If you don't know this quickly, that the 6 is 0, 1, 1, what to do? You would say, okay, I'll do the division that we mentioned. You'll divide the 6 by 2. You will find the remainder is 0. And then 6 divided by 2, the remainder is 0, and the result is 3. You divide it by 2, the remainder is 1. The result is 1, and the remainder is 1. And then you will have 1 divided by 2, and you will find the remainder. The result is 0, and the remainder is 1. And you can see here that this is even, so it's 0, odd, so it's 1, odd, so it's 1. So it's 0, 1, 1. And you remember that we do it in reverse order. So we do 1, 1, and then 0. This is the 6. Or just remember it. I can do it quickly here on the side. We can do it, for example, from the numbers from 0 to 9, which is usually are the one that you should memorize quickly. This is in decimal. In binary, you would do that, okay, this is 0, 1, 0, 1, 0, 1, 0, 1. Let me delete this. I will divide this into 4 and 4. And then again 0. So 0, 1, 0, 1, and so on, up to 9. After this, we would say 0, 0, 1, 1, 0, 0, 1, 1, and then 0, and we continue. This is 0, 0, 0, 0, and then 1, 1, 1, 1, and then we start again from 0. We will have 8 zeros here, and then we will start from. So you can see that this is 0, this is 1, this is 2, this is 3, and this is what we care about here. This is the 3, this is the 2, for example. We only care about the 3 digits here because we say, okay, every octal digit, we represent it by 3 binary digits. So we only take the 3 part. And so on. This is 4, 5, 6, 7. And this is 8. Sorry, I said 9, it's 8. So now we know that this 3, this is 2, and this is 5. This is also 6. For the fraction part, same idea. We will take this as 3 binary digits, and this 2, and this 4 is this 4. And after this, you take out those spaces. So you do the concatenation. You like compress them together to get the result. From hexadecimal to the binary base, instead of grouping them as 3 binary digits, now we have 4 binary digits. So now the 3 is this 3 here is 1, 1, 0, 0. So now it's before in the octal it has 3 digits. Now it's having to have 4. It has 4 digits. It's good to remember the following hexadecimal representations: the A, C, and F. The A is 0, 1, 0. Just remember it. The C is 0, 0, 1, 1. And the F is 1, 1, 1, 1. If you remember those 3, if you know that this is the A, the B is the next one, which is 1, 1, 0, 1. If you know that this is the C, so the next one is the D, which is 1, 0, 1, 1. If you know the F, the previous one is 0, 1, 1, 1. So just know this, and you would make it easier for you to remember the hexadecimal system. Again, I cannot enforce it. I mean, I would like to enforce this, that this table, you should memorize it. So now if you have, these are the 3 digits that I told you that you should memorize. You can see this is the A representation as 4 digits. The C is this, and the F is this. If you know the A, the B is you just put 1 more here. If you know the C, then the D is here. And if you know the F, the E, which is before that, having a 0 instead of the 1. And practice knowing the numbers from 0 to 9. This is given. You have to know directly. 9 is 1001. 6 is 0110. 5 is 1010, and so on. So what to do here is, you know that the 3 is 1100. The E, you know the F, but the E is just before, so it's 011. The 5 is 1010. The A is 0101, the one that I just mentioned. The 2 is 0100. The C is 001. And then you concatenate them together. So now to do the opposite conversion from binary to octal or hexadecimal, from binary to octal, again, you do the grouping 3-bit. From binary to hexadecimal, again, you do the same, grouping in 4 bits. Now, for example, if you have this value and you want to convert it to octal, you should convert this way. You will take those 3 together, those 3 together, those 3 together. And I made the grouping, as you can see here. Similarly, in the fraction part, 0, 1, 1, and so on. Now you might face the following point. If you group those 3 together, those 3 together, those 3 together, and those 3, you group them together. This is nice grouping. It was fitting the grouping exactly. What to do if you have one more digit? Let's say if you have only 1 here. What you would do, that you would say, okay, if there is an additional 1 here, you would say 1, and then you add 0 and 0. This is the way to do the grouping in the integral part. In the fraction part, you would take those 3 together, so it's 1, 1, 0. And then you can see there are only 2 digits here. So what you do is you add a 0 here. Why you add those zeros? Let's take an example in decimal. Look, if we say 1.5, if you write it this way, it's the same thing as 1.5. Adding zeros to the left of the integral part or to the right of the fraction part doesn't change the value of the number. That's why. So what to do after you do the grouping, and you can notice that we add this 0, you'll just convert directly those. This is 3, this is 2, this is 5, this is 4, this is 3, and this is 5, and this is also a 5. You can also check, a quick check, this way. This is a conversion to the octal base. So the numbers that you have in the result, it must be from 0 to 7. You cannot have 8 in the digits or 9 or A or B or C or D or E or F in the octal system. Now, in the hexadecimal system, we'll do the same way, but we will group 4-bit together. Every 4-bit together. You can see here that we are missing a digit, so we will add a 0. Here we add those 4 will be together, and here we have to add 3 zeros. You know that this is a 5. This one is E, this one is A, and this one is 5. Here we have 6, and we have 8. So that's the conversion from octal or hexadecimal in one hand to binary in the other hand in both ways. If you want to convert from octal to hexadecimal or from hexadecimal to octal, to do this conversion, there are many ways. The easiest one is to do the conversion via binary system. So what do you do? If you want to convert from octal to hexadecimal, do the conversion from octal to binary, and then do the conversion, this result, you do this conversion to the hexadecimal. To do this, the only thing that you should know, after you do the grouping, like every digit has 3 bits, 3 bits, 3 bits, and so on. Every digit in the octal is 3 bits in the binary. What you do is reorganize them as 4 together, 4-bit together. So you can see that we take 1, 0, 1, and this one. And now we make them 4. And then 1, 0, 0, 1. We make them 4. And then the last one, we add those 3 zeros. Similar thing on the fraction part. The fraction part, you have 0, 0, 1, and then you take 1 also from here to make 4 bits. And then 1, 1, 1, 1. And then the last one with the 3 zeros. So what we did is we have the octal number, we generate the binary number similar to the conversion that we just studied. After this, the only thing that you need to do is to reorganize the bits to generate 4 bits together. Instead of 3 bits together, it becomes 4 bits together. To do this in the correct way, always start from the point, from the radix point. So here, this is the binary point. It has 1, 0, 1 because it was generated from the octal. Now we will have 1, 0, 1, and then we'll get also this one. And after this, we'll have 1 and 0, and this 0 and this 1 to got those 4, and so on. After this, after you do this, you do the conversion from binary to hexadecimal the way that we just described. That's another example from hexadecimal to octal. So what to do here? We convert the B like this, the 6 like this. This is we described it just in the previous slides. After you do this, you reorganize by taking 3 bits together. And after this, you do the conversion to the octal number. After we finish the conversion, we will move to the binary arithmetic. We will do single bit addition with carry, multiple bit addition, single bit subtraction with borrow, multiple bit subtraction, multiplication, and the BCD addition. We will start with the easy ones, and probably we will push some of those subjects later when we have more coverage of the binary system. The single bit binary addition with carry, you are giving 2 binary digits, X and Y, and a carry, Z. We can get the sum, S, and the carry out, C, by following this table. How did we generate this table? we could say that this is the carry, Z, this is X and Y. This is the two numbers that you want to add. And we start building this table by doing the following. We just mentioned it, I just mentioned it before. 0, 1, 0, 1, 0, 1, 0, 1. The X is 0, 0, 1, 1, 0, 0, 1, 1. The Z is 0, 0, 0, 0, 1, 1, 1, 1. Now to generate the sum, you just add the 3 digits. So 0 plus 0 plus 0 is 0. And there is no carry, which is also 0. Now, 1 plus 0 plus 0 is 1 with a carry of 0. 0 plus 1 plus 0, again, it's 1 with a carry of 0. Now, for this interesting case, 1 plus 1 plus 0, we know that 1 plus 1 is 2, but we cannot represent 2 in the binary. We cannot say 2 like this. We have only 0 and 1. So we know that this 2 is 0 and then 1. This is the representation of 2. So what we did is 1. If we have 1 plus a carry, which is 0, is actually the sum is 0 and the carry is 1, which is 0, 1, the one that we just mentioned here. Now, 0 plus 0 plus 1 is 1, and the carry is 0. 1 plus 0 plus 1, we have two ones here. So it's the same way that we mentioned here, 0 and 1. 0 plus 1 plus 1, 0, and the carry is 1. The sum is 0, and the carry is 1. 1 plus 1 plus 1, which is actually 3. And we know that we represented 3 in binary as 1, 1. So that's the sum of 1, and the generated carry is 1. Another way of doing the same thing, you can add them the way that we studied long time ago in the decimal system. If you have 0 plus 0 plus 0, so the result is 0, and the carry is also 0. Trying to get the carry here and then go down. 0 plus 0 plus 1 is 1, and the carry is 0. 0 plus 1 plus 0, it's 1, and the carry is 0. Now, 1 plus 1 plus 0, we cannot say 2. So to do this, we say it's 0, and there is a carry, which is 1 in the other position. So it's 0 and 1. Now, this is in case you have a carry that's coming to you, which is 0. Now, if the carry is 1, how to add? Same idea. If it is 0 and plus 0 plus 1, so it's 1 and the carry is 0. 1 plus 0 plus 1, this is the interesting case that we just discussed, 0 and 1. 0 plus 1 plus 1, 0, and the carry is 1. Now, this is the case that is corresponding to the last line here. So it's 1 plus 1 plus 1, 1, and the carry is 1, which is 3. 1 plus 1 plus 1 is 3. Okay. So that's a single bit binary addition with carry. So let's say it with multiple bits. This is my multiple bit binary addition. So if we want to add those numbers together, how to add it? This is the addend, this is the augend, and this is the carries. In this first example here, we will say the carry n at the beginning is 0. There is nothing that just came to us. So we will assume it's 0. So you add 0, 0, and 1. The result is 1, and the carry is 0. This is what we just mentioned. 0 and 0 and 0, the result is 0, and the carry is 0. 0 plus 1 plus 0, the result is 1, and the carry is 0. 0 plus 1 plus 0, the result is 1, and the carry is 0. 0 plus 0 plus 1, then the result is 1. And this is the final result. Now, for this other example, the carry in, we assume it's 0, the first carry in. So 0 plus 1 is 1, and the carry is 0. 0 plus 1 plus 1 is 0, and the carry 1. 1 plus 1 plus 1, which is the last column, the last row in the table, is 1, and the carry is 1. 1 plus 0 is 1. The carry is 0. 0 plus 1 is 0. And the carry is 1, and it goes down here. That's what we do when we have multiple bit binary addition. And you can see this, it is super easy if you know the rules that we described in the previously in the previous slide. It's also good to mention that this position here is the least significant bit. And this one in the organ, in the addend or the organ, this is the most significant bit. You can see that if we have 5 bits added to 5 bits, the result could be 6 bits. It could be 5 bits, as you can see here, but the maximum is 6 bits. So if we have n-bit organ added with another n-bit addend, the result will be also n-bit plus possible carry out, plus 1. This is the multiple bit binary addition. If you want to do the addition in octal or hexadecimal, like for example, you have this hexadecimal value, you want to add it to this another hexadecimal value, you can do the addition in the hexadecimal base directly, but probably it's not a good idea for this course because this is an introductory course. So what we are gonna do is we will convert to binary, and then we will add using the binary system that we just described. So we convert this number from the hexadecimal to the binary this way. You can take this as an exercise. We will convert this to hexadecimal this way, and then we will add them together. To add the number, you can see that there is no digits here, so you have to fill them with 0 to get the correct result. And then you start the addition. To start the addition and you get the results correctly, you have to start from the most the least significant bit. You will start from the least significant bit going to the most significant bit, and you start adding the same way that we described. 0 plus 0. Now the carry n that you have here is 0. You will assume you don't have a carry. 0 plus 0 plus 0 is 0, and the carry is 0. 0 plus 0 plus 1 is 1, and the carry is 0. 0 plus 0 plus 1 is 1, and the carry is 0. 0 plus 0 plus 1 is 1, and the carry is 0. And you will continue. You will find out that you are just dropping those values because you are adding them with zeros. Now here, 0 plus 0 plus 1 is 1, and the carry is 0. 0 plus 0 plus 0 is 0, and the carry is 0. 0 plus 0 plus 1, now the numbers are different. So 0 plus 0 plus 1 is 1, and the carry is 0. 0 plus 0 plus 0 is the 0, and the carry is 0. 0 plus 1 is 0, and the carry is 1. 1 plus 1 plus 0 is 0, and the carry is 1. 1 plus 0 plus 0 is 1. 0, then the carry is 0. 0 plus 0 plus 1 is 1, and the carry is 0. 0 plus 0 plus 1 is 1, and the carry is 0. Notice that we jumped through the point, but we are doing the same thing. 0 plus 0 plus 1 is 1, and the carry is 0. If you add 3 zeros, it's 0, and the carry is 0. 0, 0, and 1 is 1, and the carry is 0. 0 plus 0 plus 1 is 1, and the carry is 0. 0 plus 0 plus 0 is 0, and the carry is 1. And you can see that the carry is 0. And you can see at the last one, 0, 1, 0, 0, is just adding to 0. So you drop the number. And you can see that we get the correct result. You can do the same way for the octal. You do the conversion. Notice here that we have this number in octal and this number in hexadecimal. Can you add them together? Yes. How? You convert this octal to binary. You convert this hexadecimal to binary. And then you reorganize it, because when you convert, you take 3 digits together here. And then you have 6, and the 16 base, you have 4 digits together. So what you did after this, you regroup the 8 to 4 bits and 4 bits, 4 bits and 4 bits. And the hexadecimal, you just copy it again. And then you fill the zeros in. And then you do the addition the same way that we described earlier. If you add them, you will get this result. Now the subtraction. There are 2 ways described in our class for the subtraction. There is the way that you studied before in the decimal system long time ago. I will just try to explain it to you in binary. And there is also another easier way that we will describe in the future, not in this chapter, in other chapters in the future. So the subtraction, if you borrow, there is a rule here. If you follow it, you will get the correct result. If you borrow 1 from 2 to I plus 1 from the power that is in the next position of you, it becomes 2 1s, which is 1, 1, into the power 2 to the power of I. To explain this to you, suppose that you are in the middle of subtraction, and this position here is 2 to I. So the next one here is 2 to I plus 1. Let's say that you needed to borrow from this position to this position. To borrow, what you do is you say, okay, I need to subtract 1, 0 from 1, 1. I know that I need to borrow because this is 0 and there is 1 here. 0 is less than 1, so I need to borrow. To borrow, you will get this one, you will cross it, and it will become 1, 1 in the next position. It will become 1, 1 in the next position. Now, what's the algorithm? The algorithm, you subtract the subtrahend n from the minor m. If no end borrow occurs, then m is larger than or equal to n, and the result is a non-negative number, and it's correct, and it doesn't need anything else. If an end borrow occurs, then n is larger than m, strictly larger than m. And the difference, m minus n plus n 2 to the power of n, we will discuss this later, we need to is needed to subtract it from 2 to the power of n, which means that we need to have a correction. We need to have a correction. To explain this in an example, let's say the first case, this is the first case, you want to subtract this number from this number. You can see that this is 9 minus, you can see that this is 9 minus, and this is 7. So the result should be 2. To do the subtraction, you will subtract 1. Subtracted from 1 is 0. Okay, this has no problem, and we don't need to borrow. This is 0 subtracted from 1. Oh, we need to borrow. To borrow, what to do? You will go, you cannot borrow from here because it's 0. you can borrow from this one. So what you do is, okay, you will borrow from this one. It becomes, you will cross it, and it will become 1 and 1. That's what we said here. If you cross, you will add 1, 1. So you cross this one, and it becomes 1, 1. Now, we still have the problem here. 0, you cannot subtract it from 1. What to do? We will cross one of them. We choose this one. And then we added 1 and 1. Now we can subtract. How to do the subtraction? Now, 1, 1 subtracted from 1, you can see that if you have 1, 1, and you are taking out 1, you can take those two, and the result is 1. So if we have 1, 1 subtracted from 1, the result is 1. Now going to the next digit, we already do the borrowing the previous stage. So we are left with this 1 and 0, and we want to subtract it from 1. If we do the subtraction, it becomes 0. This is the result, because 1 minus 1 is 0. And this one, we already take it out, and we borrowed it. So now we have 0 minus 0 is equal to 0. You can see that we did not take from this position. We don't have any number here. So we didn't take anything from here. So it's 0. This means that the result here is correct, which is 9 minus 7 is 2. Now, in the other case, here, we'll do the subtraction. This is just so you know, this is 4 minus, and this is 7. The result should be minus 3. We know that this is the correct result. Now, how to do this in binary? To do this, you will try to subtract at the beginning, right away from the beginning. You will try to subtract 0 from 1, and this is not possible without a borrow. So you want to borrow from here, and you can't. You want to borrow from here? Yes, you can. To do this, you will cross this one, and then you will add 1 and 1. Now what to do? You will cross one of them, which is this one, and then you will add 1 and 1. Now you can do the subtraction. 1, 1 minus 1, the result is 1. 1, 1 minus 1 is 1, because you will cross this one from this one, and this one is the leftover. This is the result of the subtraction. Now to do this subtraction, we already do some borrowing, and we have left with this one. 1 and 0. We subtracted from 1. The result is 0. Okay. Now we came here, and we found out there was a 1 originally here. We crossed it. So there is 0 here. There is nothing here. We cannot subtract 0 from 1. What to do? You will try to borrow from here. But there is a 0 here. You cannot borrow anything from there. So you will get a 1 from the last position, which doesn't have anything. You will generate this borrow, which is 1. And then you will borrow it in the next position. It becomes 1 and 1. You will cross this one, and it will become, in the next position, 1 and 1. Now, to do the subtraction here, 1, 1 minus 1, the result is 1. Now here, you have this one here, and this one, you subtract it from 0, it becomes 1. Now, from this result that we had, we know that this result is not the correct result, because we borrowed a borrow that we generated ourselves from the last position. So what to do to correct them? To correct it, you will get this result, and then you will add to it this number. So if an end borrow occurs, n is larger than m. In this case, 2 is larger than minus than 7. 2 is larger than, I mean, the 7 is larger than the 2. And the difference, this difference, should be subtracted from 2 to the n. So you take this number. This is what we got. What to do is we need this number. We say that we have this. Now we got this result. We copy it again here. And we subtract this number, which is the same digits, 0, 0, 0, 0, and then you add 1 here. You come up with this number. This number is 2 to the power of n. N here is 4. So 2 to the power of 4 is 16, which is this one. N is the number of digits, which is 4. 2 to the n is 2 to the 4, which is 16. And 16 in binary is 0, 0, 0, 0, and then 1. So you take this number and then you subtract it from 1, 0, 1, 1. To subtract this number from 1, 0, 1, 1, you do the same subtraction that we just get. You can see that we take this one out, and then you will have carries here and here and here, and you have 1, 1 here. 1, 1 minus 1 is 1, and there will be 1 here, and the 1 minus 1 is 0, 1 minus 1 is 0, and this is the result. The result here is minus the number. This number is 3, so it's minus 3. If you have a correction, means the correction means that the result is negative. Now, this is the subtraction using a borrow. So, as a subtraction note, given a two binary, x and y, a borrow z, we get the difference, s, and the borrow b. It is similar to decimal, but sometimes very hectic to do, the borrowing operation. And you can see that the borrowing wasn't so easy. The borrowing wasn't so easy to do. And there is also this correction step. So in binary, there is another way that makes it quite easy. This method is based on what we call the 2's complement representation. We will mention this later. This allows us to convert any subtraction, whatever the subtraction that we have, we convert it to addition. And we know that the addition is easy for us. So what we do, if we have a minus b, we will make the equivalence addition for it, which is a plus the negative value of b, where the negative value is generated using the 2's complement of b. Now, the 2's complement, we didn't describe it yet. We will see it in the next few slides. To subtract an octal and or hexadecimal, it's better to convert to binary first and then do the subtraction. Now, for the multiplication, the binary multiplication, the binary multiplication is very simple. If you multiply 0 by 0 is 0. 1 by 0 is 0. 0 by 1 is 0. So the multiplication is always 0 if one of the digits is 0. If you multiplied 1 by 1, this only case generates the result to be 1. And the extended multiplication to multiple digits is this way. This is an example. If the multiplicand is 1, 1, 0, 1, and the multiplier is 1, 0, 1, you can also do it in decimal. This is 5 times, and this is 11. So you know that 5 times 11, the result, the end result should be 55. So how to do the multiplication in binary, you will find it super easy. To do this, you will multiply 1 by 1 is 1, 1 by 1 is 1, 1 by 0 is 0, 1 by 1 is 1. Or simply, if you multiply any multiplicand by 1, then you copy the multiplicand in the partial product. And then you do the shift, similar to what we studied long time ago in the multiplication. 0 times the multiplicand is zeros. 1, and then you do the shift, another shift. 1 times the multiplicand, you copy the multiplicand. After you reach to this part here, you know that you do the addition to the partial product. Now this addition, we do the addition that we just studied. Those dashes is actually, you can say that they are zeros. 1 plus 0 plus 0 is 1, and the carry is 0. 0 plus 1 plus 0 plus 0 is 1, and the carry is 0. 0 plus 0 plus 0 plus 1 is 1, and the carry is 0. 0 plus 1 plus 0 plus 1, the carry, the sum here is 0, and the carry is 1, because you have two ones. 1 plus 0 plus 0 is 1, and the carry is 0, and 0 plus 1 is 1. I should mention 2 points. The first point, if you have 4 digits multiplied by 3 digits, then the product will have 4 plus 3 plus a possible 1 bit. 4 plus 3 plus 1 is 8. So this result, the product, will have up to 8 digits. For sure, it's going to be 7. For example, here is 6. So we will have 7 digits. We didn't have any carry, so it's 0. And also there is a possible 1. To generalize this, if you have n multiplicand and n bit multiplicand and m bit multiplier, the result will be n plus m plus 1 bit. So in our case, this is 4 and this is 3 bits. So the result, the maximum number of bits that you will have in the results, and this, in this case, it will be if you multiplied 1, 1, 1, 1 by 1, 1, 1. If you do this multiplication, the result might have 8 bits, which is 4 plus 3 plus a possible carry. That's the first point. The second point, you can see at the middle stages, you could add, for example, 0 plus 1 plus 0 plus 1, 4 bits together. How to do this addition? Let's have a more difficult example. If we have 1 plus 1 plus 1 plus 1 in one stage, how to do this addition? To do this addition, you would say, okay, I'll take this 3 bits only. 1 plus 1 plus 1. I know the result is 1 and carry 1. So I know that the result of those 3 is 1 and there is a carry 1. Now add 1 plus 1 here. The result of this is 0 and there is a carry 1. So we have 2 carries, 1, 1 to the next stage. In our example, we had 0 plus 1 plus 0 plus 1. It was fairly easy because 0 plus 1 plus 0, this is 1 and carry is 0, and 1 plus 1 is 0 and the carry is 1. So 2 carries is a 0. We take it out. We have only 1. That's the second point. And this is the product. Now we mentioned that this is 5 times 11, and the result should be 55. Is this 55? After we add, is this also the correct result? To do this, you would say, okay, this is 1, this is 2, this is 4, 8 is not there, 16 and 32. If you add 32 and 16, 32, 16, 4, 2, and 1, you could say that 6 and 4, this is 10, and 2, second, let me take this out. 6 and 4 is 10, so there is a carry 1 here. And you have 2 plus 2 plus 1, which is 5. And 3 plus 1 plus 1 is 5. Or you can use your calculator to add these numbers. It's also correct. So this is the correct result. And we will stop here and we will continue from this slide next time.